Bismillahirrahmanirrahim. Assalamualaikum. A very good day to you all. In this video, I'm going to talk about chapter 3.9 uniformly distributed stress. Okay. So the picture that created by artificial intelligence shows that this uniformly distributed tensile rod. Okay. This is the depiction of uniformly distributed tensile rod. Okay. Which we will discuss in this short video. Okay. This is from the 3.9 uniformly distributed stress from the chapter 3 load and stress analysis in mechanical engineering design textbook from Shigley. Okay. Uh, okay. Uniform stress assumption. Okay. Why do we need to assume and everything to become uniformly stressed? It's because it is easier to make an equation for it. So we assume the rod, okay, is uniform. Okay, it has uniform stress, although uh, in reality there will never be a uniform stress. Okay, so we assume it is a, uniform stress, so we make it easy to do the calculation, to create the formula for it. Okay, so we want to simplify stress calculation in tension. Say, uniform stress assumption used in cases of pure tension, compression, or shear to simplify stress analysis. Stress formula: stress equal to force over area. Sigma is the stress, F is the force applied, and A is the cross-sectional area. For example, steel rod in tension, a steel rod supporting a pre-section with tension applied at both ends. Stress is in uniform. Is assumed uniform. Okay. So these are the four conditions, so that we assume this in these four condition. Okay, which is the bar must be straight. Any curvature can lead to uniform stress distribution across the section. Okay, and then it is made from homogeneous material, meaning that all the material is from the same material, not mixed material. Okay, uniform stress only holds if material properties are consistent throughout. Through centroid, force must act precisely through the section center to avoid bending effects. Buckling risk in compression, a slender bar may buckle under compression. Invalidity uniform stress assumption. Okay, so this is the four assumption for it. Okay, so direction and uniform stress. Okay, for example, if we cut the metal rod using cutting boards and or bolts, the cutting is without bending. Okay, uh, if uh, if you bend something, okay, it is bending, so this is not have the uniform stress. If you cut using tools like depicted by this picture, okay, uh the cutting is not is without bending, so shearing is without bending, so this is also called uniform stress. Uniform shear stress is given tau is given by dividing center shear force V by the area A of the cross section. For example, shearing in shear metal cutting tools like thin snips produce uniform shear stress across the cutting surface is simplifying design calculation. Okay, evaluating accuracy of uniform stress assumption. Okay, stress concentration assumption and limitation for it. Stress concentration at force application points near areas near where force are applied. Actual stress distribution may differ significantly from the uniform assumption. Geometric discontinuities, continuities impact stress. Okay. Change in the geometry can lead to local increase in stress, often ignored by uniform stress assumption. Okay. What is the mean by change of geometry? Suppose you have an L shape. Okay. The place that it begins with the L, okay, it is have geometric discontinuities. Okay. Suppose they are bending, the curve, the rod is curved. So the place that is starting with the curve is called discontinuities. Okay, valid for preliminary design despite limitation. Uniform stress assumption provide useful approximation in early design stage. Okay, so we want to simplify things to make the conclusion. So at least you have some numbers that you can go for further evaluation. Okay. So that's all for the video right now. Inshallah, we meet in the next video. Thank you very much.